It's me, Sony. Welcome back to another tutorial series. Today we're going to be going through Gravity. Now, before we start, I would like to apologize. I have not eaten since 11 o'clock last night and won't be eating until 9 o'clock today. And I have already traveled 40 miles and been to work today. This is how it is every day, but it's not gonna sound like my normal self. I might sound a little bit gruff, a little bit off. I do work in a call center, by the way, so my voice is probably going to be quite used up today. That's okay, because I want to work over the weekend to actually get some more of Odyssey Experience done, and hopefully I'd even be able to release it. Anyways, let's get on with this thing. Let's go! I just wanted to do that because I like to do that. Anyways, first thing we're gonna do before we start working on Gravity is actually open the cam script, because as many people mentioned, and of course I completely forgot to do, we want to jump over to the update function and change it because it is incorrect to be the update function. It needs to be the late update function, and this is specifically for the camera. Why? Because the update function, of course, is the same one we are running in the player script, and that function can be run first in the player or first in the camera at any point. The game just decides which one to run first. So sometimes the camera can lag behind the player because the camera is being run first and then the player is being run, and then you see the update. So the player's moved when the camera should have moved last and should have seen what the player has done already. Late update is always run after the update functions of the entire program. So that means the late update will guarantee that our camera is going to move after the player moves. That's all we needed to do there. Back over to our player script. Right, so in the last video we completed our movement system, and we had what we had over here. We had the character moving with their velocity lerping towards the intended velocity here. So of course here our input magnitude multiplied by our speed at the change rate of our acceleration. Now we've done something here which could cause some real problems when we're dealing with vertical motion, gravity, jumping, right? And that is here where the velocity itself, and this is including the vertical, remember, dot y, here, dot y, and of course our velocity is our vertical motion, is also being included when we lerp. And that can't be done. Basically, gravity needs to be handled completely separate to our character movement. So what we're going to do here is actually separate them first, lerp our corrected and separate one, and then correct it again afterwards. So what we want is a duplicate of velocity, a vector 3, which is velocity x z. Now that's really useful. I like to keep it as a vector 3, although we could probably do it as a vector 2 if need be. We haven't done all of the optimizations we need anyway here. Again, copy this, velocity xz. Now we need to make that equal to velocity, and then we just take out the y. So velocity xz dot y equals 0. So now we're working with no velocity y. We're not using the vertical velocity at all. So again, now we change the one that we're lerping to velocity xz, and of course we start from xz. There we go. Now we've moved our velocity xz by all of our motion control rather than our velocity directly. So our velocity has not been affected yet by our character movement. And now on the next line, we affect our velocity. So our velocity equals, we're going to need a new vector 3 here, and in there we're going to use velocity xz dot x, dot x. We're going to use velocity dot y, which is going to be affected by the gravity and the jumping, and then we use velocity xz dot z. So we use the flat line one for x and for z, but we use the vertical from our existing velocity, which is something we've used to create the flatline one anyway. And when I say flatline, I mean flat plane. So, you know, forward, back, left, right, not vertical, not going up and down. That's what the velocity xz is for. Right, so that in itself will already work. But the reason we did that is to make sure that we can now affect the velocity.y, and you can see here it's never been affected directly. we can now affect that using our gravity and our jumping and any other vertical motion directly, and that won't be affected by our character movement. So what we can do here is get ourselves a new function. Now, we've got up here in our update function, we run our input, then we run our camera calculation, then we run our movement based on our camera input calculation. Now what we want to do, of course, our movement runs mover.move. We need to move that out so that our physical effect of the actual transform of the object, the character controller, doesn't get affected until after all of our movement code is done. And of course gravity is going to be in a separate function, so that's going to be separate to move. So what we want to do is move our character controller's move function entirely out of the do move function that we created, our custom code, so that it's being affected right at the end after we've calculated our velocity. So what we can do now, after we've calculated our positional movement by input, we can now handle gravity. So let's do gravity here. Now, what we're going to use for gravity is simply an actual gravity value. So what we want is, of course, we're going to use another physics value here, float. In fact, I'm going to do a separate little segment here called gravity. Float, grav, and we'll make it equal to 9.81 F. That is real world gravity, and we're probably not going to use that as the actual value. In fact, let me just make it nice and simple, 10. So 10 is a pretty much roundabout value that we use for gravity whenever we're simplifying in the real world. And you'll see that this is not the best to use in a platformer, but we're going to start with it because that's what we use in the real world. So our doGrav function, which of course here has not been created yet, and you can see it's highlighted but it hasn't been created yet. We're going to put down here void doGravity, and there we go. All it does is take our velocity.y and decrease it by our grav every frame. So it's essentially accelerating downwards. So velocity.y plus equals, in this case minus equals, and then we grab grav, which is of course up here. Where is it? There we are. Grav. Or we could just type it, of course, but I just want to show what we're using. So velocity.y minus equals grav multiplied by time.delta time. Remember, we're affecting it every frame, when in reality we're working with grav, which is 10 meters per second squared. So because it's per second, we're working in real world time, so every frame we're going to change it multiplied by time delta time. This is something we're doing a lot, as you can see here. I highlight it here, here, here. We're using it all the time because we want to guarantee that regardless of our frame rate, we always move things at the appropriate rate. Now this is going to work, but there's a problem. Our velocity.y is always going to decrease by gravity, no matter what. It doesn't matter whether we're grounded, it doesn't matter whether we're flying. No matter what, our velocity.y is always decreasing by gravity, which means we are going to get to infinitely large values for downward falling speed, which is insane. First thing we need to do is limit ourselves. So velocity.y, there we go, equals mathf.clamp, and then of course we're clamping velocity.y by, let's say, minus, 20 per second. Now that's a very high rate. Remember, our movement speed already is 5. That's our maximum movement speed. So let's just go with double that, in fact. Set 10, minus 10, and then of course 0 here, which of course we don't want to do as well. This is our upwards speed, and of course the negative is our downwards speed. So we're going to go with a vertical speed upwards of 10 as well. That's our maximum upward speed. Something we probably won't want to do later on anyway. We'll correct it for our jumping. The point here is we've limited our velocity.y, so our falling speed and our lifting speed if we're going up, to 10. That is also not enough, because what happens here is our player will fall infinitely up to that speed, and then he will always be falling at that speed. He's not stopping when the ground is hit, so we need to detect ground. But let's see this first we're going to set up a nice level to test this out first. So let's switch over to our game. And honestly, these things are not very visible at the moment. So I'm going to create a new material just to make everything a little bit more visible. Ground matte. There we go. So ground matte, I'm going to apply it to there. I'm going to apply it to that wall in the background. And one of the nicest little default textures that you see in Unity is this checkerboard thing. If you set yourself a nice 0.5 on there, you can now see the actual textures here a little better. If we're going to darken it a little bit as well. There. I'm going to increase that to about 0.8. And you can see now that we can see the detailing on those textures, on those checker marks. I'm going to set it to about 5.5. And now it's much more visible, the sort of edges of everything, because we don't have that glowing white now all the time. And that's useful. So we're going to make now a nice little block here. Bump-a-da-bump, bump-a-da-bump. Scale him down. Scale him down. Lift him up. There we go. There we go. A nice block there. And then we can place our character on top of it. There we go. In fact, I'm going to lift him quite high up here. There we go. So if I press pause now, as you can see, I paused the game, and then I press play, then the game will have a chance to run all of its base functions first without jumping the frame rate. And then we can press unplay here. Now watch how our character smoothly starts falling down and hits the ground. But now there's a problem, because when we fall off here, he's going to fall off very quickly. See how he moved a lot quicker than his actual acceleration. That's because his speed of falling is staying the same once he hits the ground, and it carries on falling until that 10, because we're not detecting ground.